So today we're going to talk about the Goldman-Hodgkin-Katz equation. What is Goldman-Hodgkin-Katz equation? So the Goldman-Hodgkin-Katz equation is the equation for calculating the membrane potential. It has three assumptions. First, the ion movement obeys Nernst-Planck equation, which we will discuss in when we are derive the Nernst equation. And two, all the ions move across the membrane independently. So every ion is moved independently. They are not influence each other. 3. The electrical field electric field in the membrane is constant. So if the ions across the membrane follow this three rule, it obeys Nernst-Planck equation. It is that all the ions move across the membrane independently, and electrical field in the membrane is constant. Then they fit the assumption of the Goldman-Hodgkin-Katz equation. Then you can use this equation to calculate the membrane potential. But it only has the problem that it only can use for the monovalent ions. So if you are calculating this, then you can only use for monovalent ions, which means that it can only use for calculating the sodium, potassium, and chloride, which is the main ions that are in our neurons or cardiac myocytes. So what's the equation? The membrane potential, the driving force or the membrane potential equals to F, the Faraday constant, and RT, gas constant, and the temperature, log all the P of the positive charge ion. This is the permeability, and the positive charge ion in the inside of the membrane, and the P of this positive ion outside of the membrane. Plus the probability of the anion, negative charge ion outside of the membrane, and the possibility of the negative charge ion inside of the membrane. And we have to add all the ions from I to N, from I to N, and this is from J to N. So we add all the positive charge ion with this probability together with all the negative charge ion outside the concentration outside the membrane with probability. And here is all the positive charge ion outside the membrane with the probability. and this is all the negative charge inside the membrane with what probability, and we add all of this together with log, and we can use this to calculate the voltage of the of the relative membrane potential. How do we derive the Goldman-Hodgkin-Katz equation, or Goldman equation to be short? So with this assumption, the Young movement obeys the Nernst-Planck equation, and the ion move across the membrane independently, and the electrical field in the membrane is constant. We can use it for derive this Goldman equation. So the Goldman equation is same as the Nernst equation. We need to follow 3 laws. First is Fick's law. Of the diffusion. So the Fick's first law of diffusion. We calculate the diffusion of the ions from one side of the membrane to the other side of the membrane by the concentration difference, which is the chemical gradients. So this is the chemical gradient. So what's Fick's law? Fick's law, the flow equals to this D is the diffusion coefficient, and the concentration difference. The gradient, this is the gradient of this concentration from one side to the other, from the one side of the membrane to the other side of the membrane. And then we have the Einstein relation of diffusion, which is using for calculate the electrical gradient. What's this? This has the diffusion coefficient, and is equal to the mu kt divided by q. So q is the charge of the molecule. This is the charge of one single molecule. And the mu is the mobility of this molecule. K is the Boltzmann constant, and T is the temperature. And we can change that to the mole of the molecule, so which is the mu with the gas constant, T temperature divided by the Faraday constant. So the Faraday constant is the charge of a mole of electron. So this is one single ion. This is a mole of the ion, right? So we change that to the Faraday constant here. It's so easier calculation. And we have the Ohm's law. So what is Ohm's law? Ohm's law is the Ohm's law, not the Ohm's law for the V equals to IR. Is for the drift charge particles. So Ohm's law for drift charge particle is the flow equals to minus mu z of this concentration of this particle and voltage difference of this particle. So the flux is equal to the mu is the mobility. Same as here, the mu is mobility. And Z is the valence of this particle. For example, the sodium ion has one valence, monovalence, so Z will be 1. The calcium is divalent, so the Z will be 2. And we have C is the concentration of this ion, and then we have the difference, the gradient of the voltage. So this is the Ohm's law, and then the current carried by ion is the current is equal to the valence of this ion with the periodic constant, a mole of this ion, and we have the how many current flow through this, and we have the current. So we have 1, 2, 3, 4 equations, and don't forget the basic calculus. The integration from a to b of the dx is equal to xb minus xa, the difference of the xa and b. And we have the from a integrate a to b of dx divided by x is equal to log xa xb. So with all these 4, 5, 6 equations, then we can have the derivation of the Goldman equations. So don't forget that the J is the flow, although the J here is the flow of the chemical caused by the chemical gradient, and J here is the flow caused by the electrical gradient. So we have the diffusion coefficient right here and here is the difference of the gradient of the ions. And here we have the relation of the mobility and the diffusion coefficient, and which is D equals to mu RT, the gas constant, and temperature, F is the Faraday constant. And we have the flow of the electrical caused by the electrical gradient, which is J equals to minus mu Z. Z is the concentration, and Z is the valence of the particle, and the gradient of the voltage. And then we have the current carried by the ion is I equals to ZFJ. Z is the valence, F is the Faraday constant, which is a mole of the charge of a mole of electron. And J is the flow, we just calculate from the Ohm's law. And don't forget here the basic calculus. Integration of from a to b dx equals to xb minus x1, and integrate a to b dx dx equals to log xb divided by xa. This is basic calculation, and with these six equation, we can have the Goldman equation. So we can start. So we have the Nernst-Planck equation. Another thing we need to consider about in the Goldman-Hodgkin-Katz equation is how the ion flow through the membrane. So if except the fixed first law of the diffusion, We also need to consider how the ion flow through the membrane. How to say that? So, for example, this is a membrane. And this is inside the membrane, this is outside of the membrane. Inside the membrane is a concentration. Inside the membrane, outside the membrane, there's a concentration of ion outside of the membrane. And the ion flow from the water to the lipid, there's a coefficient. There's a constant, we call it beta. So this is beta of the ion concentration inside the membrane, and we have the beta of the ion concentration outside the membrane. So this is the ion inside the lipid bilayer. This is the ion in the water, ion inside lipid bilayer. And when it flow out, you have the gradient of this ion flow from inside the membrane to the outside the membrane, and we have the beta C out, which is the ion on the other side of the lipid bilayer, but it's out on the outside, and here is the outside of concentration. So in the Goldman-Hodgkin-Katz equation, we assume that the ion concentration inside the lipid bilayer is gradually degrade in a constant. So this slope is constant. And then we have this delta C is the difference. This is delta C is the difference between inside of the membrane and the outside of the membrane. And we have the beta delta C, which is the difference of the ion inside the membrane. And then we have the flow. This is the flow of the chemical gradient, right? And then we have the electrical gradient, which is the voltage outside the membrane, and we have the voltage inside the membrane. And this gradient is on the other direction. We have the other electrical gradient. So this electrical gradient is another thing we need to know, we need to assume that this membrane, the thickness of the membrane is L. The thickness of the membrane is L. So the gradient of this, the gradient of the chemical gradient inside the membrane is beta delta C divided by L, right? And for the electrical gradient is equal to minus delta V dx is equal to V and L, right? So we assume that the voltage inside the lipid is the same as here. The voltage inside lipid is same as voltage inside water, of course. So the difference of this electrical gradient is minus V divided by L. And here we have the gradient of this ions is beta delta C divided by L. Okay, then we can start to discuss about the Goldman-Hodgkin-Katz equation. So we have this. This is the dc dx is equal to this. So the diffusion of this ion concentration, the difference of this ion concentration, you see dx is equal to this, because we assume that this is gradually decrease in a constant slope, right? It's not like a very weird shape. So we have dc dx is equal to the beta delta C divided by L. Okay. So with these two, we can start, and around we start the Goldman-Hodgkin-Katz equation is the Nernst-Planck equation. The last do another calculation is the probability permeabilities. So the drift. So the chemical gradient from the fixed law is equal to d and dc dx, right? Which is equal to the permeability of the difference between these two sides of membrane. This is the permeability. And this, we already have this from the assumed of this gradient inside the membrane. So this chemical gradient is equal to as d beta delta c divided by L, right? And is equal to P delta C. So the permeability is equal to minus D beta divided by L. And from Einstein's diffusion coefficient, relation of diffusion coefficient with the mobility is equal to mu RT divided by F. So the permeability is equal to minus mu RT beta divided by FL. So we have permeability, we have this, we have this, and we have the Nernst-Planck equation. So let's start. So the current, the J total from the Nernst equation, right? From we derive the Nernst equation, the flux of the overall flux is equal to the chemical gradient minus the diffusion of the electrical gradient, and if we turn into the current is equal to ZFJ total, right? Is equal to ZFJC minus ZFJE. So from the fixed law and the Ohm's law, we have the I is equal to minus mu ZRT dc dx plus mu z square f d dv dx, right? And the electrical field in the membrane, is dv dx is equal to dv dx is equal to v divided by L. So the current flow here, we can rewrite this into V. Rewrite this into V divided by L. Right. So we define that. We define the Y is equal to I minus mu Z square F C V divided by L. So I minus this, we define the Y equals to this and equals to this part as U Z R T D C dx. So the question will be how to remove C from equation. So we can do some integration and differentials. So we have uh, the you use some differential of this y. Y is here, so we dy dx is equal to di dx minus mu z square f b l dc dx. Then we have this, right? When we have this, we can do some calculation, and at the steady state, di dx is equal to 0 because there's the net current flow is 0. So at a steady state, we have this. So dy dx is equal to minus mu z square f v divided by L and dc dx. And then we move things around, we can get dc dx is equal to minus mu z square f v on the bottom and L on top. And then we have the dy dx. But we can have this. So let's go back to here. We have the y equals to I minus uz square fc L divided by L, v divided by L, and minus uz rt dc dx. Now we have dc dx is right here, so we can put this back to here. Then we can get y equals to minus uz rt, and then UZRT, and then the minus UZ mu Z square F V and L and dy dx. So this is equal to RTL ZFV dy dx. So when we move and then we move things around, we can get dx is equal to ZFV and RTL dy by y. So we get the dx and here, then we can do some integration. We just integrate it from 0 to L, integrate from 0 to L, and when we can get what? We can get the integrate the dx from 0 to L, we can get L, and then we can get ZFB and RTL. And when we integrate this, we can get log of y inside membrane and the y on the inside, which is L0 to L, y in the 0, y and L is y inside the membrane and y outside the membrane. you can see we have L here and L here, so we can turn this into log y in, y out equal to RT and ZFB. Okay. And then now we have now we remove all the C, right? We remove all the C in the equation. We have only Y. We can have this compare the Y inside the membrane, the Y outside the membrane. So that's this is very complicated. This part is very complicated. So let's just say we turn this into more simple. We turn this into C. We define C equals to ZVF RT. So C equals to ZVF RT. So just make this simple. So this is also equal to log Y out divided by Y in, right? And then we have this is log. So if we turn this into Y out divided by Y in, then we can get the EC. E to C equals to the Y out. Let's see, Y out. Y is equal to I minus mu Z square FC B divided by L. So C is the concentration, so the Y out is concentration outside. So we have the I minus mu Z square F so the Y out is the concentration, and inside the membrane, so we have the beta D out divided by L, and Y in is I minus mu Z square F and beta C in divided by L. So we have the Y outside of this lipid and inside the membrane. So this is our beta Cl inside the lipid by there. So and then the Y here inside the membrane. So we can get the Y in divided by Y out is equal to EC, E to C, and these complicated things. And then we just move things around, move this to here, and then we can get EC I minus mu Z square F beta by L, and we have the C in equal to I minus mu Z square F beta by L and C out. So I want to put the I together. So we have the I. So we move this to here. I of E1 minus E to C. We move the I to here, and we move this to here. So we is equal to this is minus, so equal moves this to here. Mu Z square F. Where is V? I forgot the V here. So something's missing. Something's missing. This is I'm missing a V here, so we have a V here, V here. We have a V here, V here. So here we have the V, right? So now it's the same. UZ square FCV divided by L, UZ square FC D divided by L. So we have C, E to C, and he says UZ square FV beta divided by L. So we move this to here, and we have the C out, and we have this thing inside is the minus C in to E, right? So we have this. Okay, so we have this. Let's make it more complicated. So what do we have? We have this beta thingy right here. We have this beta thing right here, but I don't like this beta thing here because we don't know the we don't know the coefficient of this ion flow from the water to the membrane. It's very difficult to calculate the beta. It's extremely difficult to find out how's the coefficient of water from the membrane from the water to the lipid bilayer. But something is easier to calculate is the permeability. Permeability is just how good is the membrane is permeable to the membrane. So the permeability, see here. What's the permeability? We have the permeability right here. Permeability is equal to mu minus mu RT beta FL, right? So we have the permeability. We have permeability here. So we have the permeability is equal to minus mu RT beta divided by F and L, right? If we multiply it with C, which is this thing right here, this thing right here is equal to minus mu RT beta by FL, and C is Z mu Z ZVF divided by RT. So we have RT cross out, F cross out. We have, so now we have DC equals to minus mu beta Z V divided by L. Okay, so we have this. We have this. So let's put it back to here. I1 minus E to C is equal to equal to T C Z F, right? And C out minus C in E. That is negative, so we have a negative here, right? E. Okay, now we have this I I 1 minus EC is equal to minus PCZF to C out minus C in EC, right? And then we can get the I is equal to all this minus P DZF C out minus C in EC, right? Divide by 1 minus E. Okay, we can have this. So in the membrane, on the membrane, we have the current caused by the potassium and the current caused by the sodium and the current caused by the chloride. If you have other monovalent ions, you can also put it here. But in the neuron or muscles, we mainly use these three ions, monovalent ions, sodium, potassium, and chloride. So it's equal to the total ion flow, total current, right? So if that is the case, then I total is equal to this, equal to minus the permeability of the potassium, CZF is C, so the potassium out, and minus potassium in EC divided by 1 minus EC minus D, the sodium's permeability, and DZF with sodium out minus sodium in EC divided by 1 minus EC, right? So only if we only put chloride here, because the Z, because if that's in another chloride is the minus P chloride D Z F of the chloride. So chloride is opposite, chloride in minus chloride out, EC by 1 minus EC. Okay, so this is I. And let's define another Y again. Let's let the Y equal to K, the potassium, plus the permeability, the difference of the permeability of potassium and permeability of sodium is sodium out, plus D K D chloride of the chloride in, and the W is equal to the inside of the membrane plus the P sodium, P permeability of sodium divided by permeability of potassium, and then this is in plus the P chloride and pK and chloride out. So with these two, we can have the I is equal to minus Z F C with PK, a permeability of Gaussian, with Y minus WEC divided by 1 minus ED. So because at the resting state or the steady state, I is equal to 0. So minus ZFCPK Y minus WEC, right, 1 minus EC is equal to 0. So these four things are the constant. These four are the constant. So we can, and this is also constant. EC is also constant. So we can have Y minus WEC is EC is equal to 0. And we can have EC is equal to Y divided by W. So this Y divided by W, Y is here, Y is here. We are very close. W is here. So Y divided by W, then we can have and then we can have this complicated thing later. So EC is equal to Y divided by W, and this C is equal to the ZVF divided by RT, right? So the E to ZVF divided by RT is equal to Y divided by W. ZVF divided by RT is equal to log Y divided by W. Then this is equal to the log so we can do it later. So we have this log divided by W. And finally, we can have the membrane potential is the V right here. V is equal to the RT ZF log Y divided by W. So this we can finally get the V is equal to the RT ZF of and the log Y is right here. Y is right here, but because Y divided by W, so we can put the PK to here, so we can have the GK Gaussian out plus the sodium out plus the chloride with chloride in divided by the P potassium in plus P potassium P sodium in plus P chloride of the chloride out. So we have this, and this everyone, this is the Goldman equation. Goldman-Hodgkin-Katz equation. From that, we can calculate the maximum potential from all the ions and the permeability of the membrane, and then we can get a membrane potential, not just maximum potential. If there's any channels open, the permeability is changed, then we can calculate the membrane potential depend on the permeability of the different ions.